So, today we shall consider various reactor configurations for carrying out enzyme catalyzed reactions. You will appreciate from the previous discussion that among the various applications of enzymes and particularly immobilized enzymes, their utilization for carrying out various chemical transformation is perhaps one of the more important sector of industrial processing. Now, this field of application is also more important from the point of view that it has an economical implication, particularly because that you have some other alternatives available, particularly in the form of chemical transformation, with which the enzymatic transformation have to compete, and therefore, the system has to be optimized to the complete level up to the complete plant design. Now, a major feature of the while the major feature of the whole process will include the enzyme immobilized enzyme preparation itself, but over and above you will also need some kind of a hardware, an equipment in which the immobilized enzyme or for that matter even soluble enzyme can play around and catalyze the reaction, and the proper design, proper choice of a proper configuration of these enzyme reactors is therefore very important, keeping in view the whole process economics, and which plays in addition to the catalytic function of the enzyme, the whole operation will be controlled economically by even the choice of the reactor. Now, essentially a number of reactor systems that are available, they can be classified in a very general way on the basis of their mode of charging and discharging of the substrate and product stream. I mean, you are familiar, for example, in a laboratory experimentation, a simple stirred vessel, for example, in which you take a beaker, for example, you put it on a magnetic stirrer, or you can also attach to a I mean you can also insert a mechanical stirrer if you want, and this magnetic stirred material, then you can add the enzyme particles into it, and the substrate can be fed to it, and the reaction can be, and of course, you can control the pH and temperature of the reaction, and you can carry out the reaction in the laboratory. Now, basically here the mode of charging and discharging the substrate is once, you initially feed the enzyme as well as the substrate, and at the end of the reaction you take out the final product, and of course, enzyme is mixed with it. If it is soluble enzyme, if it is an immobilized enzyme preparation, you can filter it or centrifuge it to recover it back. So, that is one of the probably the most simplest configuration that is possible to carry out an enzyme catalyzed reaction. Now, the two basic factors on which the classification of enzyme reactors can be based is essentially on the mode of charging and discharging of the substrate and product stream, and also physical configuration, what is the shape of the reactor. For example, it is a column, it is a stirred vessel, or it could be like a I mean sort of ultrafiltration cell, or whatever kind of configuration is available, that also can be used, and keeping in view a very broad classification can be given on the basis of batch reactors and continuous reactors. And of course, the kind of reactor system that I described a little earlier in that for experimental purposes, they fall under batch category. That means essentially the batch reactors are essentially very suitable for small scale experimental studies, mainly because that they are simple in construction and operation, and they do not need any supporting structure, unlike in the case of let us say for example, continuous reactors, where you need to feed the substrate stream continuously. So, you need a pump. Similarly, at the outlet you also need a pump to withdraw the product stream, whereas in the case of a batch reactor, essentially you just initially charge the reactor and continue then under reaction conditions, and then discharge the reactor at the end of it, do cleaning operation. So, no supporting structures are required, and therefore, they are very simple, and therefore, they find a very I mean common application in the small scale experimental studies. And now, in the case of a soluble enzyme, in this case the enzyme cannot be separated. So, therefore, basically most of the enzyme reactions that require crude enzyme preparations, where no degree of purification is needed, in most cases, particularly in cases where for food or beverage productions the soluble enzymes are added, and they carry out the reaction and they go along with the product stream, and the enzyme is not required to be separated. However, if we use immobilized enzyme preparation, the separation of the enzyme is feasible by filtration or centrifugation, and you can reuse it. In fact, even batch reactors are used in commercial preparations extensively, mainly because of their simplicity and ease of fabrication and operational convenience. For many reactions, one typical example is the hydrolysis of penicillin to 6 amino penicillinic acid 6 APA, which is an intermediate for ampicillin. This is usually done in a repeated batch reactor using immobilized enzyme, and the immobilized enzyme is retained in the reactor either by providing a mass for filtering the enzyme to be retained in the reactor, or it can be sort of strained after the product stream has been recovered. Now, batch reactors also have a important feature for use with the soluble enzymes, because most of the continuous enzyme systems are not very suitable. Of course, there are options where even soluble enzymes can be used in a continuous reactor, but for almost practically most applications the use of soluble enzyme is usually with the batch reactors. And the third feature in favor of batch reactor is the use of insoluble substrates. While in the case of continuous reactor, the use of insoluble substrate, particularly using immobilized enzyme preparations, is not feasible, particularly in terms of reactions being carried out by solid contact, which is difficult. Most of the enzyme catalyzed reactions which involve insoluble substrates, the batch reactor systems are very ideally suited. Now, for example, I mean just to illustrate with the example, the insoluble substrates are like hydrolysis of cellulose. Now, cellulosic materials are insoluble and the enzyme has to be reacted with this insoluble substrate to hydrolyze into glucose. Starch hydrolysis also a similar behavior. Gelatinous, of course, it is not particulate insoluble like particulate matter, but still it is in the form of a gel, and after you cook the starch you get a gel, and the gel has to be reacted with the soluble enzyme to carry out the liquefaction. Now, among the batch reactors there are mainly two types of configurations that are very commonly used. One is stir tank, as I mentioned in just recently, where you use almost like a tank with a stirring facility. Now, very often for small scale operations you can have this stir tank with it jacketed for temperature control. On a large scale you can also have coils inserted into the reactor, whereby temperature control can be monitored. Another advantage is even you can have devices for addition of acids or alkali if pH control is the requirement of the reaction. I mean, for example, in the example I cited a little ago on the hydrolysis of penicillin to 6 APA, because of acid production, simultaneous acid production, you need to control the pH, otherwise the enzyme gets inactivated, and a very precise control of pH is needed, and therefore addition of the alkali simultaneously is a must, and which can be carried out very easily in a stirred batch reactor. And of course, with a control system you can control the pH, and of course, as a matter of fact, very often the extent of reaction there is also can also be monitored by the quantity of alkali consumed, because after all stoichiometrically the quantity of acid produced is same as the extent of conversion of penicillin to 6 APA. The other modified form is a packed bed reactor, particularly when we are talking of immobilized enzymes, and the enzyme is now in the form of either spherical particles, globules, chips, membranes. Then you can pack them into a column and make a packed bed, and the reactor can be operated in a batch mode by total recycle, in the total recycle mode. Now, if you look at some of the for example, in the case of batch reactor as I showed. Now, the second, in the case of recycle reactor, if the product stream, product outlet is closed and the total enzyme is then recycled back into the feed, and it can be carried out, the whole operation can be carried out over a period of time, which is the batch reaction time. It can act as a batch immobilized enzyme reactor, where with a total recycle, packed bed with a total recycle, and of course, the only sort of constraint or the assumption here will be to be considered from the quantitative point of view as a batch reactor or as a perfect mixed batch reactor will be that the recycle time of the substrate must be very small compared to the total batch time. For a perfect total recycle reactor to be considered as a batch reactor operation, and the requirement should be that the total recycle time must be very small or negligible compared to the total batch size. So, that recycling has to be very fast. So, that all the enzyme is in contact with the, in the case of batch reaction at any given time all the enzyme must be in contact with the total substrate feed. So, to achieve that the recycle time must be very small or the recycling has to be very fast, and therefore, these two kinds of reactor systems are very commonly used as batch reactor. The second category, and probably which is of more significance to us as in the case of immobilized enzyme systems, are continuous flow reactors, because as a matter of fact the whole purpose of, one of the major purpose of immobilizing enzymes is to use them in continuous mode or repeated mode. Of course, you can use the batch reactors also in case of repeated mode, but more conveniently they can be used in the form of immobilized enzymes in continuous reactors. Now, continuous reactors, three major classes of continuous reactors are listed here. You have continuous stir tank reactor, and the classical feature of a continuous stir tank reactor, as you can see here, again it is a type of a stirred reactor in which you give a continuous supply of substrate in the form of feed, and the same volume at the same rate the product outlet, the product stream is taken out while retaining the immobilized enzyme preparation in the reactor stream. Now, a major characteristic feature of the continuous stir tank reactor, often designated as CSTR, is that the contents of the reactor are perfectly mixed or the system is totally homogeneous. That means, the concentration of any particular species in the reaction system is uniform throughout the content of the reactor, and this concentration is same as that in the outlet stream. The concentration of any species of a reaction system is homogeneous, same at every point in the reactor, and that is equal to the concentration at in the product stream, because it is a perfectly mixed system. Now, this characteristic makes a very unique situation, and you will appreciate when our contents in the reactor are at the same composition as in the product stream, it implies that the concentration of the substrate in the reactor is at a level which is present in the outlet stream. For example, if we want to carry out a conversion of let us say 95%, leaving behind 5% substrate, that means the concentration of the substrate in the reactor will be only 5% of that of the feed inlet. So, the effective concentration of substrate at which the reaction is taking place is much smaller than the substrate inlet stream concentration, and therefore, such reactions you will also appreciate will be ideally suited for the enzyme catalyzed reactions which are strongly substrate inhibited, because the effective substrate concentration in the reactor will be much lesser than the actual substrate concentration in the feed stream. So, the inhibitory effect will be totally masked. On the other hand, if the reaction is inhibited by the product, then such reactors are essentially not very suitable, because the content in the reactor will also have a very high product concentration at any given time. So, therefore, the reaction will always continue in a product inhibited regime. So, the reaction rate can be very slow. So, therefore, the reactors in the form of continuous stir tank reactors are ideally suited for substrate inhibited reactions rather than product inhibited reactions. So, that is one feature, and which I wanted to highlight. Then if you come back to your continuous reactors, the second category is plug flow reactors. Now of course, plug flow reactors incidentally, or in a much broader sense if you can say packed bed reactors, are probably one of the most commonly used types of reactors in the immobilized enzyme applications. Of course, mainly because of the nature of the catalyst, because it is usually in the form of either particles or films. It can be easily packed into the system and can provide you a very high catalyst density, enzyme density in the reactor system. And obviously, higher the catalyst density, the overall reaction rate can also be very high, because what you are doing is the enzyme concentration per unit volume will be much higher compared to a CSTR. Now, but the basic characteristic of a plug flow reactor essentially, as you notice here, is that the substrate inlet stream moves with a flat concentration profile or velocity profile along the length of the reactor. Or what I am trying to say, that if suppose you consider say an enzyme reactor, this is the enzyme reactor, a plug flow reactor, and then if you consider the central axis, the velocity profile of the feed, this is your S G naught S, this is the product stream, the concentration profile of the feed at any given cross section of the reactor is flat. That means, there are no axial dispersions, and so the velocity profile of the feed stream is throughout the length of the reactor is flat, or in other words basically that the feed inlet, the feed stream moves almost like a plug, and therefore, the name that what we talk about as a plug flow reactor, basically broadly they are essentially packed bed systems, and they can be operated. Of course, achieving a perfect plug flow condition may not be I mean feasible in large scale reactors, while in the case of small scale reactors, while by manipulating or by increasing the length to diameter ratio, one can achieve a much better plug flow behavior. But in the case of large reactors, there are a lot of deviations from the plug flow behavior, which of course we will consider, they can be accounted in while we consider the reactor performance. The third category of the continuous reactors are fluidized bed reactor. Now, they are essentially somewhere in between the continuous stir tank reactor and plug flow reactor, and basically if you feed, if you put the substrate feed at a speed high enough to lift the bed or fluidize the bed, but not allow the catalyst particles to go out of the reactor. Of course, unlike in the case of a packed bed, as you notice that there is a static bed of the immobilized enzyme particles, and the feed is the flow rate, the linear velocity of the feed is not large enough so that the bed can be disturbed, and the composition of the characteristic of the bed can be sort of theoretically accounted, numerically accounted by voidage, what we call as a factor called voidage epsilon, which is essentially the void volume in the bed divided by the total packed bed. And of course, this will be a function of the particle shape and size. Particle shape and size will control the voidage in the packed bed, but when you move ahead from the plug flow behavior and increase the continue to increase your feed velocity stream to a level that the packed bed is disturbed, it gets fluidized. The particles are fluidized in the reactor system, almost like as shown here in the reactor, and but not to the extent that the catalyst particles are driven out of the reactor system. They are retained in the reactor system. We call it fluidized bed of an fluidized bed immobilized enzyme reactor. Now, basically such reactors in terms of fluid dynamics, they probably provide you a performance somewhere in between the CSTR and PFR, but are ideally suited for reactions which have a requirement of good heat and mass transfer, because in case of many of the situations like in packed bed, the heat and mass transfers may be very difficult, and particularly in case of reactions which are exothermic in nature, there might be a lot of local hot spots which can inactivate the enzyme. And of course, fortunately in the case of enzyme catalyzed reactions, the reactions are not highly exothermic, they are usually isothermal, and therefore the problem of heat transfer is not so severe, but still there are some even a smaller level of heat generated can be taken care very easily in case of fluidized bed reactors, or alternatively if your substrate is highly viscous or it is, let us say, colloidal in nature. In those cases also a fluidized bed reactor can provide you a much better system for carrying out immobilized enzyme reactions in a continuous mode. Now, these are the three major classes of continuous reactors, but as a matter of fact in practice a number of hybrids of these reactor systems have been proposed by people, both in the case of CSTR as well as in the case of plug flow reactor. In fact, fluidized bed reactor itself is a hybrid between the two major classes, but even under CSTR a modification which has been proposed is in the form of your CSTR coupled with a ultrafiltration cell. Now, particularly in case where you want to carry out reactions using insoluble substrates or soluble enzymes a CSTR and want to use a continuous reactor. Now, obviously for a soluble enzyme you cannot use a plug flow reactor. So, a CSTR coupled with the ultrafiltration reactor can be easily used for carrying out reactions with the soluble enzyme or with insoluble substrate.
Why can't we use a plug flow reactor?
In the case of soluble enzyme, the use of plug flow reactor you will drive away the enzyme simultaneously and you cannot use it continuously. Now, in the case of a CSTR you can use a soluble enzyme or along with a soluble or insoluble substrate by carrying out in a CSTR and coupling the CSTR with the ultrafiltration module. That is the reactor output, instead of going directly to the product stream, passes through ultrafiltration unit in which the product stream is sort of filtered out and can be taken out as a product stream, while the retentate which contains mainly our enzyme is recycled back into the reactor. So, it is a form of a recycle reactor, just like we saw in the case of total recycled packed bed, which operates as a batch reactor, or even in some cases even as a continuous reactor a recycle reactor can be used, where part of the output stream is recycled and part is taken out as a product. In this case here again we do the same thing, a part of the output stream which is the filtrate from the ultrafiltration unit is taken out of the product stream, and the retentate of the ultrafiltration unit is recycled back into the reactor and it can be operated in a continuous reactor. So, overall performance wise in terms of the reactor performance it can be almost considered almost similar to that of a CSTR. Now, there are two major modifications which have been proposed in the case of plug flow reactors. While the conventional systems, as we have seen, you use a packed bed and feed this substrate at the either at the top of the column or at the bottom of the column, either of the combination is feasible, but they also may have some operational problems. The two major modifications of that which have been proposed and have been used in the enzyme catalyzed reactions, one is a hollow fiber reactor. Now, in the case of hollow fiber, the system is something like a cell and tube reactor, cell and tube heat exchanger type of situation, where you have very fine capillary type of fibers which are semi permeable, in which the enzyme can be entrapped. The enzyme feed is put in the hollow fibers and the main feed substrate is passed to the cell side on the tube side, cell side, and now because of the semi permeability of the hollow fiber membranes, the substrate and the enzyme can come in contact. That means the substrate can go into the vicinity of the enzyme and product can go out, and ultimately the product stream can be taken out, but the enzyme cannot go out of the tubes, of the ultrafiltration tubes, and such a reaction system has an advantage that again such a system you can use as a continuous plug flow reactor even using with soluble enzymes. While a packed bed system cannot be used with soluble enzyme, but a hollow fiber reactor can be used with soluble enzyme, and particularly where the sort of contacting a enzyme and substrate is a problem, such reactors have been used. And in terms of flow behavior, because of these hollow fibers being of the capillary size, very fine capillaries, and a bundle is made, so they almost provide you a reactor performance in line with the plug flow
The
behavior.
center, is it the fluid flowing?
Pardon?
The center, is it the fluid flowing? So the
No, in the tubes, in the hollow fiber tubes, capillary tubes is the enzyme contained, and in the annular in the space provided between the tubes and the cell is the substrate feed is fed into it. In fact, in,
the diagonal line.
you are referring to these ones.
No, the one that is just beginning of the left side.
Left side.
Left.
Left side circle.
That's
This one,
Yeah.
This- this one,
Thing projecting out. The thing projecting out on the left.
this one.
On the left hand side.
No, I have.
Its head has something written down.
You see, this is only a cross section of the system. In fact, all the tubes essentially at the top are joined in a section, so that they come out in the same section. This is only a cross section shown here, I mean in the expanded form.
The small round hollows are the fibers or the
Yeah,
diagonals?
no, these dresses,
No. In the cross sectional diagram that you have made.
yeah, the circles which you are seeing here,
Yeah.
they are blown up here in this form,
Acha.
and they are just they indicate one hollow fiber.
Acha.
So essentially the whole the reactor consists of a bundle of hollow fibers. Almost about 80 or 100 hollow fibers can be constituted in about 1 square inch. I mean of that order, hollow fibers. And
Sir, in this case, is the enzyme immobilized on the fibers?
well, it can be. There are systems in which reported are there on the tube walls, the enzyme can be immobilized. But alternatively, in a general fashion, it can also be in the form of soluble enzyme, which is passed through the. Of course, when you are immobilizing on the walls of the tube, then they don't operate really as a hollow fiber reactor. Then it is almost like a packed bed reactor on which the tube on the tube side. I mean the tubes are used as a matrix. Tubes are used as a matrix, and it is almost like a packed bed reactor. It doesn't matter whether you pack it in a horizontal fashion or a vertical fashion. The tubes are used as the immobilizing matrix. Whereas I am talking about that the enzyme is used in soluble mode, is retained in the semi-permeable hollow fiber tubes, so that it is not able to go out, almost like microencapsulation, almost similar to microencapsulation, where the enzyme is contained within the instead of spherical capsules in the form of tubes. The other noble modification of the plug flow system is a spiral membrane bound module. Now it is a very specific configuration which has been reported and of course has been used industrially, and that's why I thought I like to. You see, in this what they do is this has been first of all is this system has been used extensively for preparations, immobilized enzyme preparations, which are in the form of thin films, and the typical application which has emerged is where the enzyme is immobilized on collagen matrix in the form of thin films, and you get a very long roll. It can even also be used along with your fiber entrapped enzymes, if the fibers are woven in the form of a cloth or things like that. So you get a very large surface area in the form of a film, long film. Now what is essentially done is this thin film of the enzyme containing enzyme is bound spirally onto a central core. You take a central core and on which spirally the enzyme sheet is wrapped around the core, and of course in between, to provide strength, there is a matrix, or there is a kind of a porous sheet which can keep the two enzyme sheets separated. Of course, it serves two purposes. One is that it provides strength to your membrane, the sheet, the enzyme sheet, and the other is it also doesn't doesn't allow the enzyme system to get clogged. So now such a system, and then it can be packed into a column, into a tube, and obviously such a system also can provide a very high enzyme loading, because the surface area available on the thin film is very large, and therefore it can provide you very high enzyme loading, and also the system performs almost like a plug flow reactor.
So it's a substrate.
No, it operates like almost like a packed bed. Packed bed system. Only thing, instead of packing the column with the particulate material, what we are doing is the film is being wrapped around a core spaced by another sheet, and then the whole sort of core is inserted into a column. So either you can feed the substrate either from the top or the bottom and take out to another stream. It's almost like a plug flow reactor. So these are some of the config. Of course, I must say that this is not the comprehensive list of the type of reactor that has been reported. A very large variations of reactor designs have been reported. Even for example, in the case of a CSTR, people have immobilized the enzyme onto the blades of the impellers and carry out the reaction. So there are a variety of configurations have been used. But of course, some of them are purely of academic interest also. But by and large, from the fluid dynamics and the reactor performance point of view, they have to be classified in one of those standard operational modes. Now, just to sum up the variety of reactors, the type of reactors that are available, you must notice that the combined continuous or continuous stirred flow reactor with the ultrafiltration system is useful with the soluble enzyme or along with the immobilized enzyme. Particularly when insoluble substrates are required to be handled, or colloidal substrates are required to be handled, because in the handling of colloidal substrates, plug flow reactors often find difficulty with the plug flow reactors. So the combined CSTR coupled with the ultrafiltration reactor can be easily used. Now, of course, such reactors have been very poor in terms of long term operations, mainly because of the adsorption of the enzyme onto the membrane surface. Well, most of the membranes provide a good adsorbing surface, and the enzyme get adsorbed onto that, and the reactor performance is deterred during continuous use. Now, of course, concentration, polarization, all the defects or all the limitations of an ultrafiltration system will also be associated here. The reaction system will have to face all the problems like concentration, polarization of an ultrafiltration system, and unless those are taken care, the reactor performance will be adversely affected. Now, in the case
long-term operation, it's the absorption of the.
Yes, one is that the system undergoes a very fast rate of deactivation. Mainly because of you have to transfer the substrate, the whole material along with the substrate into the ultrafiltration module and recycle back the retentate. So during that all transfer, there is significant loss occurring. And as a matter of fact, you must also appreciate, and in most of these, one of the reasons of inactivation is also shear inactivation. And if you handle, particularly in case of even CSTR, many of the enzymes or the carrier particles that are shear sensitive or can undergo a lot of carriers which can undergo a lot of attrition during use, the CSTR becomes a sort of a disadvantageous system, because if the carrier particles get disintegrated during use, it will involve the loss of enzyme. Now, in the case of CSTR, I think the most favorable point is, as I mentioned, one favorable point was that for reactions which are substrate inhibited, CSTR is a desirable feature. The other desirable feature of CSTR is that it can be used wherever pH control is required, because it provides you an open configuration in which the pH control can be easily, pH monitoring and control both can be exercised, which is very difficult in the case of a plug flow reactor. Either you in the case of plug flow reactor, you have a recycle system, and so that I have an external loop in which the pH monitoring and control is exercised, or otherwise in an ideal plug flow behavior the pH control is difficult. But the CSTR can provide you an ideal tool where, and in many cases of immobilized enzyme reactions, pH control is a requisite. Then of course in the case of CSTR, even colloidal or insoluble substrates can be processed, which is not feasible in the case of plug flow behavior. Then of course easy replacement of catalyst compared to while in the case of PFR or the plug flow reactor, the regeneration of carrier is simple, because after the reactor the immobilized enzyme is exhausted, one can sort of stop for a while, regenerate the carrier, re-immobilize the system and reuse. But in the case of, if suppose the carrier cannot be regenerated and it has to be replaced, the replacement of carrier is much simpler in the case of CSTR. And of course we have talked about higher yields for substrate undergoing higher yields for reactions undergoing substrate inhibition. Then in the case of plug flow reactors, often it has been noted that the conversion efficiencies are much higher compared to CSTR, and the major reason for that are two. I mean, broadly speaking, we can discuss, we will see that the quantitative analysis of reactor performance in both the cases, but the major reason is, one is that most of the enzyme reactions are inhibited, if not very excessively but mildly, by product concentration. So the plug flow behavior almost optimizes, it maximizes or minimizes the product concentration at any given point. The maximum product concentration is only at the outlet stream, but in the reactor length, during the across the reactor length, the product concentration is much lesser than the outlet stream, as against the opposite happens in the case of a CSTR. So the reactor performance is much better usually in the case of PFR, and the second reason is that the enzyme loading per unit volume is much higher in a PFR compared to in a CSTR. In the CSTR, the concentration of enzyme which you can administer usually is not very high, and compared to a PFR. Then the fourth category or the other category of enzyme reactors, fluidized bed reactors, as I mentioned earlier, are much better suited for heat and mass transfer characteristics, freedom from plugging. Very often if colloidal substrates are to be used, a plug flow reactor faces problem in terms of, I mean, so plugging or choking of the column. A fluidized bed reactor can be easily, insoluble substrates can be used. Pressure drop is another problem in plug flow reactors, because if the particle size, if we want to, let us say, eliminate some of the problems associated with the internal pore diffusion in the system, the particle size has to be reduced, and reduction of particle size will mean increasing pressure drop across the bed, and increasing pressure drop across the bed ultimately, I mean, puts a economic barrier in terms of higher energy consumption for feeding the substrate. And therefore, in the case of fine particles, very fine particles, the low pressure, you can handle the system in a fluidized bed reactor without much pressure drop problems. Of course, one of the disadvantages is that the power requirements for fluidizing the bed, because you need to feed the substrate at very high speed, very high linear velocities, with requiring much higher power, larger power consumption. And of course, the scale up of the fluidized bed reactors has also been very largely empirical. I mean, the scale up systems are more empirical compared to CSTR and PFR, which are considered to be idealized reactor systems, because in terms of fluid flow behavior, they represent the two extremes. In one, there is no axial dispersion; in the other case, there is a complete back mixing. So, and therefore, their modeling or their arriving at the reactor performance is much certain, much more defined, and therefore scale up can be easily carried out, whereas in the case of fluidized bed reactor, scale up is more empirical.
So why is it low pressure drop in the case repeated? Low pressure.
Low pressure drop in the case of? There will not be much pressure drop essentially, because I mean, in the case of, just like in the case of a packed bed reactor, the particles are all compact. So obviously when you feed a substrate, the pressure drop will be very large if the particle size is very fine. In the case of a fluidized bed reactor, the voidage is very high. The voidage is almost approximating to that of CSTR. towards, I mean not the same of course, but it is approaching to that, and therefore there is no pressure drop. The system has a very large void edge, the void edge increases. Then of course, if you look at, I mean if we, before we go into the reactor performance of different types of reactors for the immobilized enzyme systems, I think we should normally cannot consider all the parameters like non-ideal fluid dynamics, the mass transfer constraints, and along with the biochemical reaction we cannot really combine at one stage. We can take up those issues one by one, and to begin with we can only consider an idealized enzyme reactor system, whereby I mean we would like to make certain assumptions before we go into the reactor performance, and the assumptions are that first thing we are assuming that the reactor undergoes an isothermal operation. That means the reactor the delta H value of the reaction is not very high, so there are no I mean sort of temperature gradient in the reaction, the first assumption. And of course uniform enzyme distribution. Of course in practice, even if you see the immobilized enzyme preparation themselves, there are reports that even in the immobilized enzyme preparation itself there are no uniform enzyme distribution practically, but I mean for theoretical purposes we assume that the enzyme is distributed uniformly in the reactor, whether it is a plug flow reactor or is a batch reactor or a CSTR. The third condition is we are assuming either a plug flow behavior for packed bed or a completely back mix behavior for CSTR in terms of fluid dynamics. We are not considering anywhere in, even that means even fluidized bed is not considered as an idealized reactor system. So we are considering the two extreme conditions, either a plug flow behavior or a completely back mix system. Then we are also ignoring external film or internal pore diffusion limitations, if any. We are considering that there are no diffusional limitations, that means the rate of reaction is much slower than the rate of diffusion is fast enough. Then the last assumption is that there is no significant partitioning of substrate between bulk and the carrier phase. Now if the system follows such, we can solely evaluate or conduct a reactor performance on the basis of biochemical reaction, the reaction kinetics, and to do so the major reactor design parameters which have to be considered are listed here. The first one is tau, which is the reactor space time in terms of the V upon Q, where V is the reactor volume and Q is the flow rate in the case of a continuous reactor of course, and this tau in the case of a batch reactor is the batch reaction time. Then you have initial substrate concentration, another parameter which we have to define. In any problem of a immobilized enzyme or soluble enzyme reactor, we must define the S0, the batch time or the reactor space time in continuous reactor. Then total enzyme concentration in the system. Of course, when I say E0, I think it will be desirable to also have the magnitude of Kd, the deactivation constant, depending upon the, particularly it will be more important when we are talking of continuous operation, where the reactor operation times are large enough, the deactivation constant will also play a key role. Then the temperature of operation, because deactivation also will depend on the operational temperature, and I think I would like to mention here that most enzyme reactors, continuous enzyme reactors, are usually operated a little below their optimum temperatures, just to increase or reduce the Kd value and increase the operational half life. Then pH, of course pH here is not only monitoring, but I think more important is the control of pH. How are you exercising control of pH? Then fractional conversion in the reactor, which is can be defined as S0 minus S upon S0, that means the concentration difference, substrate concentration between the inlet and the outlet stream, the ratio of the two. Then the reactor productivity is another parameter which is important, X S0 upon tau. X S0 is the total product formed and tau is the space time, so per unit time, the amount of product formed per unit time. Of course, if we consider S0 as a concentration term, so it becomes per unit volume also. Then is the reaction capacity, reactor capacity. Now although under given set of conditions you may get certain kind of productivity, but the reactor capacity will be given by the Vm, the K2E0 of the reactor of the enzyme multiplied by the reactor volume multiplied by the void edge. Of course here even in case of tau also we can multiply it by void edge if you want to consider a broader picture of a packed bed reactor, because this V reactor volume is not the packed bed volume, it is the volume of the fluid in the reactor. So obviously the total bed multiplied by the void days will give you the fluid volume in the reactor. In the case of CSTR, void days can be considered almost equal to 1, because the volume occupied by the carrier is very small compared to total reactor volume. Then you have reaction capacity can be given by K2 E naught, which is Vm, multiplied by the reactor volume and the void days, and then of course finally the important parameter is enzyme kinetics itself, because the reactor performance will depend upon the reaction kinetics which controls the reaction. Mind it, we are not considering under idealized reactor conditions anything like diffusional limitations, partitioning effects and non-ideal fluid flow behavior, which we will consider subsequently one by one to arrive at the final reactor performance.
What is PR?
So what is PR?
Productivity, reactor productivity, and CR is the reactor capacity.